In the previous lesson, we analyzed the I/O behavior of a very simple algorithm to compute the average in a two-dimensional array. In this lesson, we're going to do exactly the same thing, except that we're going to look at an algorithm that computes the average by scanning over the array column by column. And as we will see, this is going to make a huge difference in the number of I/Os. Okay, so let's have a look at the algorithm. Here's the algorithm. As I said, it simply scans over the array row by row, adds all the values it encounters, and then divides the total value by the number of cells in the array. To analyze the I/O behavior of this algorithm, it's important to know how the blocks are formed. So here we assume that the array is stored in row major order. So that means that the blocks are formed in the following way. Right? Row by row, so the first 3 items, so here in this example we assume the block size is 3 for simplicity. The first 3 items on the first row are in one block, the second 3 are in the second block, and then maybe the remaining one plus something of the next row is in the next block, and so on. Now let's see how the algorithm proceeds, and in particular let's see how many blocks it is going to read while executing this algorithm. Okay. So the algorithm is going to start in this corner and, well, the block containing this data element is not yet in the internal memory, so we have to read this block. Then we go to the next item in this column. Again, the block containing this item is not in the internal memory, so we have to read the block. And this continues for a while. We need another block, we need another block, and so on, until at some moment the memory is full. So now we need to read in another block, but, well, here in this small example, the internal memory could hold 5 blocks, and we already have 5 blocks in the internal memory. So before we can read the block that we need, we have to throw out, we have to evict one of the existing blocks. And let's assume that the block replacement policy is simply least recently used. So that means we're going to evict the block that we didn't use for the longest time, which in this case was the first block we read. So we write this back to the external memory, and now the memory is no longer full, and we can read the next block. Okay, good. So we go on to the next item, and the same situation occurs. The memory is full, we need to throw out a block, then we have space to read the next block, and so on. Okay, so this continues, another step, memory full, need to read, throw out a block, read the next block, and so on. But now let's see what happens when we go to the second column. Okay, so here's a block that we actually already read before. But in the meantime, we've thrown the block out of our internal memory, so that means we have to read this block again. And what you see is that actually at every step in the algorithm has to read a new block, because even if we already used the block before, then, well, by the time we want to use it again, we already evicted it, so we have to read it again. This is under the assumption that the main memory size cannot hold all the blocks from one column. So you need a pretty big matrix for this, of course. So if you read a new block at every step, well, the matrix size is n, which is m by m, so we're going to do n I/Os. And if we compare this to the row by row algorithm, well, it's actually pretty bad, because the row by row algorithm read only n divided by b blocks. It read every block exactly once, but now we need n I/Os, n read operations. So that's worse by a factor of b, and remember that in practice the b is a couple of hundred, maybe even more. So that means that maybe the first algorithm, the row by row one, needs only a few seconds, but the second algorithm is going to take minutes, or if it's a really big matrix, then maybe the first one needs minutes and the second one really needs hours and hours. So we now understand why it's extremely important to take the I/O behavior into account when you're dealing with data that does not fit into the main memory. So what we'll do next time is we're going to look at two types of algorithms. One is an algorithm that actually needs to know the amount of memory that you have available and the size of the blocks. Those are called cache-aware algorithms. And the other type of algorithm, and that's similar to the one that we saw before, it just works without knowing the main memory size and without knowing the block size. But that's for the next lesson.